Welcome to The Explainer. Today, we're going to break down a fundamental concept that engineers and physicists use every single day. It's a way of looking at any push or any pull and seeing what it's actually doing. It might sound a little technical, but I promise, by the end of this, you are going to see the world around you in a completely new light.
So, let's kick things off with a little puzzle we've all experienced. Picture this. You're pulling a rolling suitcase through an airport. You're pulling that handle up and at an angle, right? You're doing one single action, just pulling. But the suitcase is actually doing two things. It's moving forward along the ground, and it's also being lifted up a tiny bit, just enough to keep the wheels rolling smoothly. So how does that work? How can one single pull do two completely different things at the same time? Well, that's exactly what we're going to solve today.
But before we can solve that puzzle, we've got to be on the same page about what a force even is. I know we use the word all the time, but in physics it has a very specific and actually a pretty simple definition. At its heart, a force is just a push or a pull from one thing on another. That's it. But to really get it, to define it completely, you need to know three things. First, how strong is it? That's its magnitude. Second, which way is it going? That's its direction. And third, where exactly is the push happening? That's the point of application. You nail those three down and you've got the force totally defined. Let me give you a really simple analogy. Imagine I told you to get to a coffee shop that's 5 miles northeast of here. That's one simple, diagonal instruction. But you'd get to the exact same spot if I told you to first go 4 miles east and then make a left and go 3 miles north. It's two separate, simpler steps that get you to the same end result. And believe it or not, that is exactly what we're doing with forces. We're taking that one diagonal pull on the suitcase and breaking it down into its east and north parts, or in our case, its forward and its upward parts.
Right. And this awesome process of breaking down a force into its simpler parts has a name. It's called resolution. And this isn't just some neat party trick, it's a super powerful tool that lets engineers solve some incredibly complex problems.
We're going to focus on what are called rectangular components. Now, that's just a fancy way of saying we're splitting a force into two pieces that are at a perfect 90-degree angle to each other. You know, like a horizontal part and a vertical part. And the reason we do this is super simple. It just makes all the math so much cleaner, so much more predictable, and honestly, way easier to deal with. And this image, this slide right here, really makes it all click. Take a look at that main arrow, the one labeled F. That's our original diagonal pull. But see how you can imagine its shadow on the horizontal line below? That's Fx. That's the part of the force that's only pulling to the right. And you can do the exact same thing for the vertical line. That's Fy, the part that's only pulling up. It's still one force, F, but it's doing two jobs at once. And Fx and Fy tell us exactly how much muscle is going into each of those jobs.
Okay, so that's the big idea. But how do we find the actual values? You know, how strong are Fx and Fy? Well, the answer comes from a tool you definitely learned back in math class, trigonometry. And don't panic, we only need two little functions, and it's easier than you remember.
Think of it like a simple recipe that works every single time. First, you just identify your main force, F, and the angle it's at. Second, you picture that right-angled triangle, where your force is the longest side. And then, and this is the key part, you just have to remember two little rules. To find the horizontal part, Fx, you multiply the force by the cosine of the angle. And to find the vertical part, Fy, you multiply the force by the sine of the angle. That's really it. Cosine for horizontal, sine for vertical.
All right, enough with the theory. Let's put this recipe to the test with a real, concrete example. This is going to make those formulas crystal clear.
So here's the setup. We've got a force of 60 newtons, that's our magnitude, and it's being applied at an angle of 35 degrees up from the ground. Our mission, should we choose to accept it, is to figure out exactly how much of that 60 newton pull is going sideways and how much is going straight up.
Let's just follow our recipe. For the horizontal part, Fx, we take our total force, 60 newtons, and we multiply it by the cosine of 35 degrees. You pop that into a calculator and, boom, you get 49.15 newtons. So, out of our total 60 newtons of effort, a solid 49 of them are dedicated purely to moving the object horizontally.
And now for the vertical part, Fy. Same deal. We take our 60 newtons, but this time we multiply it by the sine of 35 degrees, which gives us 34.41 newtons. And there it is. That one single 60 newton diagonal pull is doing the exact same job as pulling sideways with 49.15 newtons of force and pulling straight up with 34.41 newtons of force, all at the same time.
Okay, That was pretty straightforward, right? Now let's level up and tackle a classic engineering problem where this whole idea is just absolutely essential. An object sitting on a ramp, or as engineers call it, an inclined plane.
So in this problem, the main force we're dealing with is the block's own weight, a hefty 200 kilonewtons. And here's the thing about weight. Gravity always pulls it straight down, towards the center of the Earth. But obviously the block can't go straight down. The ramp's in the way. It can only slide down the ramp. So the real question becomes, how much of that 200 kilonewton downward pull is actually turning into a force that wants to make the block slide? Now this is where things get really clever. Instead of our usual boring horizontal and vertical axis, we're going to tilt our whole point of view. It's like tilting your head to look at a picture. We're going to define our new x-axis as running parallel to the ramp, and our new y-axis as being perpendicular to it, pointing straight into the ramp. Now, why on earth would we do that? Because it makes the problem 1,000 times easier. The only ways the block can move are along the ramp or into the ramp. By lining up our axes with the problem, the math just works.
Now, because of that clever little tilt we did, the jobs of sine and cosine actually swap places here. The part of the force that's trying to slide the block down the ramp, down our new x-axis, is now found using sine. So we take the 200 kilonewtons of weight, multiply it by the sine of 30 degrees, and we get a nice clean 100 kilonewtons. That's it. That's the force that's trying to pull the block down the slide. It's the force you'd have to push against to keep it from moving.
So what about the other piece? Well, the force that's pushing the block directly into the surface of the ramp is now found using cosine. So 200 kilonewtons times the cosine of 30 degrees gives us 173.2 kilonewtons. And this isn't just some random number, this is super important. This is the normal force, and it's what you'd use to calculate friction. So by resolving one force, weight, we found two incredibly useful, completely different things. The force making it slide and the force causing friction. Pretty cool, right?
Okay, let's zoom out for a second. What's the big takeaway from all of this? What have we really learned? Well, you've basically just been handed a new superpower for seeing the hidden physics that are happening all around you.
The bottom line is this. Any force that's acting at an angle can be broken down into simpler 90-degree components using sine and cosine. It's this one simple idea that lets us take messy, real-world problems and analyze them in a really clean, manageable way. And as we saw with that ramp, you can even be clever and tilt your whole perspective to make a problem even easier to solve. It's a game changer.
Look, this isn't just an exercise from a textbook. Understanding how to do this is literally the first step in designing a bridge that won't collapse, engineering the suspension for a car, or even figuring out the trajectory of a rocket. You now have the fundamental skill to look at any push or pull and deconstruct it into what it's really doing. So the only question left is, what complex problem are you going to solve first?